So first of all, I would like to thank Tufik and his co-organizers for, of course, for inviting me to this conference, but of course, also for organizing the conference itself. I think that in those days of global warming, it's something like 35 degrees today in Bordeaux, which is far too much for September. It's a very nice way, this conference, of keeping posted of what's happening in our fields without traveling all around the planet. So thank you and congratulations for holding these virtual conferences.
Welcome.
And so this being said, so I'm going to talk about certain posets defined on Dyck paths. And if you attended Richard Stanley's talk on the first day, I have to tell you that this will be far less poset theoretic than Richard's talk. In fact, I will focus on the description and counting of intervals in those lattices. Okay, so let me start with a very hard definition, Dyck paths. Well, you probably all know what a Dyck path is. So you have up and down steps. They are attached to some kind of surface here, and the path cannot cross this surface. What I call the size is the number of up steps. By the way, if you happen to have questions, you can, of course, use the chat, but you can also stop me. That's fine. And I will need the notion of a valley in the Dyck path. So that's a sequence down, up. You have two valleys in this path. And then in most of my slides, these Dyck paths will be rotated by 45 degrees. So they now consist of north and east steps, and they lie above what I call the base path, this light blue path, which is northeast repeated n times. And this is what the valley becomes. Now, in addition to these familiar paths, we'll also, in fact, consider sometimes just arbitrary paths or walks consisting of north and east steps. Now, in real life, when you start thinking about paths and walks, you very often need to have a map. And what happens is that in this combinatorial context, well, the same holds true, except that the maps that we need are a bit different from this one, but just as nice. So let me define now the other main characters of my talks, which are planar maps. So a map is just a graph, or more precisely a multigraph. That is, I allow multiple edges like here and loops here. And so this graph has to be connected planar, and we give it with one of its proper embeddings in the plane. By proper, I mean that the edges cannot cross. And two maps are considered the same if you can deform continuously one into another. But for instance, if I take this little loop here and draw it here instead, I have the same graph, but a different map. Because if I want to go from one to the other, I have to create edge crossings. So this is not the same map. And our maps, of course, they have vertices and edges, as graphs do have. And in addition to that, they also have faces, which are, like here you have one face, they are the connected components that are left if you remove edges. And these faces have a certain degree, so that's the length of the boundary. So here this face has degree 1, 2, 3. And there's a big outer face around the map here. Now you may have noticed this little edge here, this little thing pointing here at the corner. This is because we consider only rooted map, and this means that we distinguish a certain corner in this outer face around. This prevents maps from having symmetries, which is always a problem when you want to count them. And my last definition on maps is that of a triangulation. And here you just want all faces including the outer face, 1, 2, 3, to have degree 3. Okay, so here's an outline of my talk. I will mostly describe 3 families of posets, 2 of them being lattices. So that's the blue sections. And there will be a little interlude where containing something like a proof, a sketch of a proof, where I will describe some recursive constructions for the intervals in some of these lattices. And I want to show you which kind of functional equations they give rise to. So let me start with my first lattice, which is sometimes called Stanley's lattice, for instance, by Don Knuth. So I'm very happy to stick to this terminology, even though I noticed on Monday that this is not one of Richard's favorite posets. So anyway, let me define them. So you have a poset for each size n, and it's a poset on Dyck paths of size n. And the order relation is very simple. You say that a path u is less than another path v if it lies below. So for instance, well, this black path here is certainly below this kind of maximal path there. And in blue, I always draw the staircase, the base path, above which you must be. So the covering relations in this poset, they are very easy to describe. You just take a valley, east-north, and you swap the 2 steps, just forming a peak. For instance, here, there's this valley, and you swap it into a peak, and you get there. And in particular, if you fill the cells below these paths, you will realize that this is just a sublattice of the Young lattice of partitions. And in particular, it is a graded lattice. Now, since we all like to count, well, there's many things that we can count in this lattice. Of course, the number of elements is the Catalan number, 100. You may also want to count the number of covering relations. So this is the number of purple edges here, the edges of the Hasse diagram. In this case, it's 5, 2, but in general, it's a binomial coefficient. So really, the number of covering relation is the number of Dyck paths with a marked valley, because you have a covering relation per valley. And then we will be mostly interested in counting intervals. And by an interval, I really mean a 2-chain. That is a pair of comparable Dyck paths, like these 2 thick paths here. And more generally, we may consider p-chains in this Stanley lattice. So if you choose, say, a p-chain, here a 3-chain, and move the 3 paths a little bit apart, you will get a configuration of paths that do not intersect. And as you probably know, we have wonderful techniques for counting such configurations of paths, namely the Lindström, Gesell and Vienno and others determinants. So for instance, the number of such 3 chains will be given by a 3-by-3 determinant. And in some cases, in particular, when you consider P by P determinants, you may also want to use Christian Kratenthaler's Bible on determinant calculus. So this doesn't seem maybe too complicated, at least for intervals, that is, pairs of comparable Dyck paths.
There is a question from the audience.
Yeah.
Do you allow repeats in the chains or not?
Sorry?
Do you allow repeats in the chain? Are these multi-chains?
Yes. So in other words, if an interval could be reduced to just one path. That is, if I take twice this blue path, it forms an interval, which is reduced to the path itself. But so the inequalities do not need to be strict.
Okay.
Yeah. Thank you. So here, if I get back here, well, you probably see here the 2x2 determinant that is counting these configurations. It has a nice formula. And then a nice product formula was worked out by Christian, Tony Gutmann, and Xavier in a different context for P chains in general, with a nice asymptotic behavior. And there you have a connection, as you can probably feel, with some tableaus, in this case with symplectic tableaus. Now, this sequence is well known to the OEIS, and it counts several kinds of things. So, for instance, certain loops in the quadrant, which are in fact trivially equivalent to pairs of non-intersecting Dyck paths. It also counts some Young tableaus, and it also counts some maps. More precisely, it counts certain triangulations which are decorated with something called a Schnyder wood. So I won't get into the details of the definition. I have basically one picture. This is a triangulation, and its inner edges are partitioned into three trees, the blue one pointing north, green one pointing west, and a red one. And in addition to that, you want certain rules to be respected around every inner vertex. So I won't get into the details, but what's maybe remarkable here is that this structure was not designed originally, I think, by combinatorialists, but it arose in a problem of graph drawing. This Walter Schnyder, he wanted to draw planar graphs of size n on a grid with straight lines without edge crossings, and he wanted to know what the smallest possible grid was. And then later, Nicolas Bonichon decided to count these triangulations equipped with a Schnyder wood, and he found the bijections with what? With pairs of non-intersecting Dyck paths of size n, hence this formula. So I have an example here. Maybe I won't get into the details. Here you have the Stanley lattice when n is 3, and you can count that there are 14 intervals. And if you take these Schnyder woods with the right multiplicities, accounting for the various symmetries, then you get 14 as well. Okay, so now, so far, we've ordered Dyck paths by containment. But if instead of taking as a base path the stair, northeast, northeast, and so on, in fact, we can take any path, for instance, this one. Let's call it V. And then you can consider the set of paths that lie weakly above V and have the same endpoints. So in a sense, they are attached to the base path V. And you can again order them by containment. You get another piece of the Young lattice, and I call SV, like Stanley V, this lattice. And to choose your base path, there's several natural possibilities. We had seen the stair, which gives rise to Dyck paths. You could also take what I call a hook. So you have east paths followed by north paths, and that's it. And then your elements are just all paths going from, say, 0, 0 to ij. Another choice that will come back in my talk is when V is this kind of M stair. So you have an up path, M east, an up step, M east, one north, M east, and so on. And so the paths that lie above this base path are called M Dyck paths. So here you have a 2 Dyck path. That's another choice that you'll see very often in my talk. And then we can again try to count things. First of all, we can try to count the elements. So this is counting walks above a given base path, V. So when V is arbitrary, I think that the best answer that we have is a determinant due to Creveras a long time ago. When V is just a hook, that is east, north, while you're just counting all paths that end at ij, this is a binomial coefficient. When you count m-Dyck paths, that is the number of elements in the corresponding posets, you find these Foucault-Catalan numbers. So these are some examples, but we will be again mostly interested in counting intervals in these lattices. And so here is again one such result. So you're taking this as your base path, this kind of M stair with n up steps. And so you want to count, I should have drawn a picture, you want to count pairs of non-crossing paths above this one. And again, it is given by a Gesell-Vienno determinant, and you have a nice formula, which is the counterpart of what we had formerly for Dyck paths when M was 1. And here I think it's appropriate to ask some questions. So first, I don't know if there are M analogues of the Schnyder woods for these numbers. That would be interesting. And then it would be worth trying to get the corresponding result for P chains. I didn't try to work this out, but it might be feasible. So this is for this specific base path. Now, when your base path is arbitrary, I don't know of any nice formula, but what we'll often do is to sum the number of intervals in the Stanley lattice S B for a whole family of walks of base path V. So here, for instance, I'm summing these numbers over all paths that end at position ij. So you see here in blue, I have my base path. And above it, these two paths form an interval in the corresponding lattice. So in total, this sum is counting configurations of 3 non-crossing paths, going from this point to this one. And this, again, we know how to count by a 3-by-3 determinant, and here's the numbers that you get. So again, these numbers, they occur somewhere else. And in particular, they count certain permutations called Baxter permutations, which were counted a long time ago. And more recently, it was realized that they also count some maps, namely maps equipped with what is called a bipolar orientation of the edges. You probably guess what this means from this picture. And there's a slightly funny story to tell about these numbers, namely the first person who tried to count such maps is a famous theoretical physicist named Rodney Baxter. And he used recursive decomposition, functional equations and whatnot to get these numbers. And he didn't know Baxter numbers, he didn't know Baxter permutations, but he just had the same name as the original Baxter with a different one. And he stumbled on the same numbers. And then many people found lots of nice bijections relating Baxter permutations, these triples of paths, and bipolar orientations of maps. So this phenomenon is very well understood. Okay, so I'm now coming to my second family of lattices, which is maybe more mysterious. They are called v-Tamari lattices. And they are included in the v-Stanley lattice in the following sense, namely that the elements will be the same, and it's just the order relation that will be different. And any order relation in Tamari, the Tamari coset, is also an order relation in the Stanley coset. So let me be more precise. So the original Tamari lattice was defined by, of course, v-Tamari. It can be defined on various objects like binary trees, but here I'm sticking to Dyck walks, Dyck paths. So I take again the set of Dyck paths having n steps, and I will define this poset by giving its covering relations. So here you have a path U, and again, you will have a cover of U for every valley. And so here, what I do, so I pick a valley, so this one in U, and I start from the bottom of this valley here, and I look, so then I have an up step, and I look at the shortest Dyck path that follows this point here. So this is the pink one here. If I add this, I get another Dyck path, but it's not the shortest one. So I take this one, and in the covering relation, I swap this blue east step with this pink factor here. So the pink path moves one step to the left, and in particular, I think it's quite clear that this new path V lies above U in the Stanley lattice. What else? So let's take an example. Here are again the 5 Dyck paths of size 3. You see this poset is no longer graded. Here I jump by 2 in a sense. And let's see what happens for this Dyck path. So it has just one valley. And to compute its cover, so I swap this path with the shortest Dyck path that follows, which happens to be not that short. It's the whole remainder here. And so I jump directly to here, whereas in the Stanley lattice, I was just swapping these 2 steps and jumping here. Okay, so that's the original Tamari lattice. And very recently, or somewhat recently, an extension was defined to walks lying above any V, so not necessarily a stair. And this was constructed by Louis-François Préville-Rattel and Xavier Ville. So I want to tell you what the covering relations will be for a general base path V. But first, in order to tell you, I have to reformulate a bit what happens in the original Dyck case. So I told you that to construct a cover corresponding to this valley, you swap this path and the shortest Dyck path that follows. Another way of describing this point here of the path, where you have to cut, is to look at the horizontal distance between the bottom of the valley and what I call the forbidden area. So everything that lies below the base path. So this distance is t, here it's 2. And then I move along the path and look at the next point that is a distance d from the forbidden area, and it's this one. And so this is another way of describing this point. And then I do the swap. So now with this formulation, you can use it as well when the base path is something different, not necessarily a stair. So here, so this is in light blue, my base path. Here I have a path above it with a valley. So the distance between this point and the forbidden area is 4. And then I look at the next point at distance 4 of the forbidden area. It happens to be this one. And in this v-Tamari order, I will swap the blue step with this pink path here. So this forms for each v a lattice, as was proved by Louis-François and Xavier. And this lattice has been revisited since then, for instance, in this paper, but there are other papers. So let me show you some pictures. So here is my v, my base path. Here is the original Stanley lattice, where you were just replacing valleys by peaks. And here is the more sophisticated v-Tamari lattice. And so let's see if I am able to describe something. So you see what changes is, for instance, this, which becomes this. And so this happens if I look at this dark path. I take this valley and I look at the shortest Dyck path that follows it. It consists of these 2 steps. And so I swap this with this and I get directly here. And here you have another difference with the Tamari lattice. Now there's several, as I said, several natural choices for the base path. If I take a hook here, so let's see what the covering relations are. So here is a valley. It's at distance d from the forbidden area. The next point that is at distance d is in fact just this one, just above the bottom of the valley. So in this case, I'm just replacing a valley by a peak, which is also the covering rule in the Stanley lattice. So for this V, the 2 lattices, Stanley and Tamari, they are in fact the same. Another, probably more interesting choice of the base path V is this generalized m-stair. So you define the Tamari lattice on m Dyck paths. Here you have an example. And in fact, this generalization arose before the paper by Préville, Rattel, and Vienno in some work by François Bergeron and Louis-François again, which is in algebraic combinatorics. And there are wonderful connections between the intervals in these lattices and certain co-invariant spaces of polynomials in 3 sets of n variables. So this is an attempt to generalize to 3 sets of variables the wonderful story that has been developed for 2 sets of variables with all these diagonal harmonics and wonderful conjectures. And it seems that in this context where you have 3 sets of variables, the Dyck paths are replaced by intervals in the Tamari lattices somehow. So, and this is in fact how I got interested in these lattices, because François was more than 10 years ago advertising some conjectures about the number of intervals in these things. And this was my first incursion on this topic. And so quite a few years ago with Eric Fusy and Louis-François, we proved this conjecture, saying that, so if you take this m-stair as your base path and look at the corresponding Tamari lattice, the number of intervals that you get, which depends on n, number of steps, and m, is given by nice binomial times n plus 1 divided by 2 linear terms in n. So here are these first numbers. When m is 1, that's for the Dyck case, 2 Dyck, 3 Dyck, and so on. Now, if you've ever seen or played a bit with a planar map counting, you will know that the map literature is just full of formulae that look like this one. So here are some formulae for counting all maps or cubic or bipartite or whatnot. And so you see they have the same form, a binomial divided, sometimes you have an nth power, and divided by two linear terms in n, as on the previous slide. In particular, this one, which counts certain triangulations, is in fact the number of intervals in the usual Tamari lattice. So this one is crying for bijection, and indeed, this result that we proved using recursive constructions has a bijective proof, but only in the case when m is 1. That is for usual Dyck paths. And by the way, in this case, the formula is was proved earlier by Frédéric Chapoton. And what's very nice is that this bijection is just a specialization of the bijection I mentioned before by Bernardi and Bonichon between what we had before. So beforehand, we had the Stanley intervals, pairs of paths, one below the other, and triangulations with this Schnyder wood, whatever this is. Now, all Tamari intervals, they are in particular Stanley intervals. Of course, the converse is wrong. And so if you specialize this bijection just to Tamari intervals, which triangulations do you get? Well, you get once each triangulation, or in other words, you get a triangulation equipped with its canonical Schnyder wood. So really, this means that this original bijection has a lot of structure. And now, so when m is larger than 1, essentially, we don't have a family of maps at hand that we would know to be counted by these numbers. However, Fusy and Humbert have constructed bijection between these intervals and some maps, but somehow this result is the only way of counting them. Okay, and now, as in the Stanley case, the total number of intervals in the v-Tamari lattice TV, so total, I mean summed over all base paths v ending at the prescribed point, and here I'm also summing, in fact, I'm fixing the total length n of the paths. So this question has been investigated as well by Wenxie Fang and Louis-François. And so at first it seems like a complicated problem because you have all these v-Tamari lattices, but in fact, this boils down to counting just some intervals, not all, in the usual, in the ordinary Tamari lattice on Dyck paths of size 1 more. And this comes from a property that was proved in this paper, but that I'm going to illustrate by stealing a picture in that paper, which is the following. So let's see if I try to explain this. So here on the left, you have the usual Tamari order on Dyck paths of size 4. 14 elements. Here is the order. On the right, you have the collection of v-Tamari lattices for all v's of length 3. So there should be 8 of them, 2 to the 3. And as you can see, there is a way to partition the Tamari order on the left into intervals in such a way every v-Tamari lattice here occurs once. And also the way to partition is rather easy to describe. So really, when you want to count the intervals in this collection of 8 lattices, what you need to do is to count certain intervals, that is, those that fit in a block, in the usual Tamari lattice. So these intervals are called synchronized. And, well, this is doable both recursively and bijectively. And this is how Wenxier and Louis-François found, again, a nice map formula for the total number of these intervals. And in fact, there's a refinement where you just fix the endpoint of the base path. And these numbers, they are known to count non-separable planar maps with fixed number of vertices and faces. Okay, so that's another very nice occurrence of maps in Tamari intervals. Now comes my little interlude. So I keep talking of bijections with maps and so on and so forth, but the original proofs, they were not bijective, and there are still some results that we do not know how to prove bijectively, especially when m is larger than 1. And the original proofs, which are in a sense more robust, they are classical recursive proofs. And I want to sketch one of them and to show you what kind of functional equations they lead to. So let me focus on possibly the simplest problem. You take the Tamari lattice as defined by v-Tamari. So this is on Dyck paths, which I have rotated back here. So the base path is just the usual stair. And I want to count intervals in this lattice. So here is supposedly a typical interval. So the top path is purple and dark blue, and below you have the smaller path, which of course lies below. And we're going to decompose this interval into 2 smaller intervals and use this to write, say, recurrence relations. And to do this, we look at the top path, and at the first time, it returns to level 0. So, of course, the bottom path has to return to level 0 at the same position. And to the right, what you have is a smaller Tamari interval. Now, to the left, you also have a Tamari interval, but it has a very strange property, namely that, well, strange, I don't know, but it has this additional property that the top path only touches the boundary, the horizontal boundary at its endpoints. The bottom path may touch this boundary earlier, so this is the first return to the origin. And what we do is that in this pair of paths, so we delete in the top path the first and last step. So in other words, we smash, we push this top path 1 step lower. And in the bottom path, we just push lower. We delete, say, the first step and the one that returns for the first time to the boundary. So we move down the purple part and the green part. We record the position where this down step was. So this is what this little arrow is telling you. And the theorem tells you that in this way, we have defined a bijection between non-empty Tamari intervals and pairs consisting of a Tamari interval and another one in which one of the contacts of the bottom path with the boundary is distinguished. Okay, so I don't tell you why this is true, but it is true. And what it should tell you is that if you want to use this to count your intervals, you will have to consider, in addition to the size, a new parameter, a new statistics, which is the number of contacts that this bottom path has with the boundary. And so this means adding a new variable, which Doron would call catalytic. And so this is what we did. So we have now a generating function that depends on two variables, x and t. So the t records the length, or the half length of the paths. And then for every interval uv in the Tamari lattice, tn, you have an additional weight, x, to the number of contacts that the bottom path has. And then, well, believe me, but this is not hard, this bijection translates into this functional equation, which tells you that f is this x corresponding to the empty interval, plus this term. So here this f of x stands for this interval. And here the fact of choosing a contact and lifting back the green part is encoded by what I call a discrete derivative or a divided difference, f of x minus f of 1 over x minus 1. So this is what I call delta f, like derivative. And this kind of equations, you find them all over the place if you count planar maps. Now, in our work with Eric and Louis-François, we did the same for m Dyck paths, so for the m-Tamari intervals. We have a similar decomposition with more marks. And again, the two variable generating function satisfies a nice looking equation, but where this delta operator, or more especially f of x times delta, is applied m times to the series itself. So it's a nice compact form. I can show you, for instance, when m is 2, so for two Dyck paths, here is the equation that we have. So we have here discrete derivative, and f prime of 1, that's the derivative with respect to x evaluated at 1. Okay, so how do we solve this? Well, in principle, there is this result that we proved with Arnaud Géhan some years ago that tells you that the solution of this equation, and in fact of any well-founded discrete differential equation, is an algebraic function. That is, it will satisfy a polynomial equation. And when m is fixed and small, we also have a technique for solving the equation, that is finding the minimal polynomial of f of x. But in this case, m was generic, and what we ended up doing was to guess and check the value of f of x. And in particular, when x is 1, so we're just recording the size of the intervals, we got the nice numbers that I've shown already. So this is typical of these kinds of problems with intervals, Tamari intervals. And now, finally, I want to move to the most recent collection of posets, which are no longer lattices. They are called greedy Tamari posets, and they are subsets of the Tamari posets. They were introduced very recently by Aram Dermanjian. And now here is the rule for the covering relations. So I will start with the case where the base path is just a stair. So I pick a valley. And beforehand, I was looking at the shortest Dyck path that follows it. Now I'm looking at the longest Dyck path that follows it. So I go up to here and I do the swap. Now, another way of describing this point is to say that, starting from here, this is the first point that is at the same horizontal distance of the forbidden area, and that is such that I can't go further. That is, it is followed by an east step, which is at a strictly smaller distance from the forbidden area, or this may be also the final point of the path. And once things are described in this way, there's no reason why you wouldn't do it with a generic base path. So here in light blue, I have a valley, and it is the bottom of the valley is at distance 4 from the forbidden area, and I follow the path. This is larger than 4, larger than 4. Here I have my first point at distance 4, but I don't stop here. This one is also at distance 4, and it is followed by an east step at distance only 3. So I stop here, and I swap this pink path with the blue one, with the blue step. So here are some examples. So for instance, for Dyck paths, so here is the usual Tamari order. Here is the greedy version. So you see it's no longer a lattice. I have 2 minimal elements. So let's see if I can describe what's happening here. Let's see, I'm looking at this valley. The longest Dyck path that follows is this entire path of length 4. And so I swap it with this down step, which makes me jump directly here, whereas in the Tamari order, I was doing that in 2 steps. And here's another example with a different base path. And you see something similar happens here when I look at this valley here, I think. And well, the only result that's recent, and I want to show you on these greedy v-Tamari lattices, deals again with the number of intervals in the m-Dyck case. And we found with Frédéric Chapoton, again, a nice map-like formula for the number of these intervals. And again, our proof is recursive, and you have a catalytic variable, not the same as before, and one of these discrete differential equations that we solve by guess and check. But now what's nice here and different from the non-greedy case is that we know what these numbers count in the world of maps. And in fact, we proved many years ago with Gilles Schaeffer that they count certain maps called m+1 constellations. I'm not sure I will give you the whole definition. They are bicolored maps. The faces are black and white. And then all black faces have the same degree, here 3, and the degrees of the white faces are multiples of m+1, that is here of 3. And of course, there's this question of now finding a bijection between greedy m intervals and m+1 constellations. So I will jump to my final remarks. In fact, the first one builds on the previous observation, because we have a much stronger conjecture. In fact, it seems that these greedy intervals, say VW, in these intervals, the collection of ascent sizes, so if you look at the number of ascents of given size in the top path W, this is distributed like the collection of degrees in the white faces of the constellations. And in addition, the first ascent should match with the degree of the root face. So this is a very strong, I have no doubt that this conjecture is true. And what's nice is that for the constellation problem, we already have a functional equation, which was obtained by Wentier in his thesis. And so you see, so X is counting the degree of the root face, and you have an operator that's applied m times, and you're recording all face degrees. This is somehow the counterpart of the discrete difference operator. So what we need to do now is to understand this functional equation on greedy intervals. But at the moment, we don't know how to do that. And this is reminiscent also of something that we did on usual Tamari intervals with Guillaume Chapuis and Louis-François. Now I will finish. That's another nice question, deals with the Q analogs of these countings, and this is especially relevant in this algebraic context of diagonal harmonics. The Q records the length of the longest chain in your interval, and you have some kind of Q derivatives, but similar looking equations. And since I'm slightly running out of time, I've listed all kinds of questions that, depending on your taste, you may want to explore. I think they are interesting. What could I say? In this work, there's a fourth kind of poset, Creveras poset on Dyck paths, which is a subposet of the Tamari one. I don't know if it has V counterparts. You can explore asymptotic properties of random intervals. There are these very interesting Cambrian lattices defined by Nathan Reading, which seems to have the same numbers of intervals. So there's a lot to do, and I will stop here. Thank you for your attention. This tree is what we call in French un Tamari. Okay, thank you.